In this video, we are going to focus on how to evaluate whether a chemical is an agonist, a partial agonist, an inverse agonist, a competitive antagonist, or a non-competitive antagonist based on a dose-response curve. The learning objectives for this lesson are to identify the different types of ligands and to interpret the dose-response graphs associated with each ligand type and understand how drugs or toxicants can modify endogenous ligands. The next few slides are organized similarly. Here is the dose-response curve of an agonist. The agonist, represented as a green dot, is able to bind and activate receptors, represented in blue. Once bound, the agonist causes a functional response. The ability to produce a response is termed efficacy, or intrinsic activity. An example of a response would be an increase in cyclic AMP. The curve on the right side of the slide illustrates the characteristics of an increasing dose of an agonist and the measured response. The y-axis represents the response measured, and the x-axis represents the log concentration of the agonist. With increasing concentration of agonist, there is a sigmoidal response, meaning at low concentration of agonist there is not enough ligand to generate a response, followed by a linear portion where an increase in agonist results in a proportional increase in response, while at very high concentrations the receptors become saturated and there is a diminished increase in response for a given increase in agonist. Now let us examine the action of a competitive antagonist on the response of an agonist. Both the agonist and the antagonist bind to the same site on a receptor. The competitive antagonist is represented by a yellow dot. When the competitive antagonist binds to the receptor, there is no response, whereas when an agonist binds, there is a response. Once again, the response of the agonist alone is shown on the dose-response graph on the right. In contrast, when a constant amount of antagonist is added to an increasing concentration of agonist, the dose-response curve is shifted to the right. This is illustrated by the orange arrow. The degree of shift to the right is related to the affinity of the antagonist and the dose used. The higher the dose of antagonist, the more agonist is needed to overcome the response. You can imagine affinity as the strength of antagonist-receptor interaction. More agonist is needed to interrupt this interaction when affinity is high. It is important to recognize that the response of the competitive antagonist is surmountable and that the maximum response remains unchanged. Now let us look at what happens when you add a non-competitive antagonist to increasing concentrations of agonist. The non-competitive antagonist is represented as a purple square. When the non-competitive antagonist binds the receptor, it is unable to activate the receptor, but blocks the ability of the agonist to bind. The dose-response curve with the yellow arrow represents what happens as you increase the amount of agonist. The action of the non-competitive antagonist cannot be overcome by increasing the dose of agonist. This is because the agonist and antagonist binding sites are different. Hence, the agonist will not displace the antagonist molecule. With increasing concentrations of agonist, the receptors that do not bind to the antagonist can become bound by agonist and elicit a response. However, an agonist cannot displace an antagonist molecule that has already been bound to the receptor. Thus, some of the receptors are permanently blocked by the antagonist and a full response cannot be reached. Here is an example of a dose-response curve of a partial agonist. Partial agonists result in less than full response. You can see that even though all receptors are bound, there is only a partial response triggered, and therefore, even at high concentrations of partial agonist, the response is never 100% of what a full agonist would elicit. An example would be buprenorphine, which even at high concentrations will never trigger a full response of the mu-opioid receptor like morphine will. Inverse agonists are ligands that, when bound, decrease a response to below the basal level of activity of a receptor. An inverse agonist has all the properties of a full agonist, except that it elicits the opposite to that of a normal agonist. Or in other words, it demonstrates negative efficacy. As the common definition of inverse agonists become clear, more and more molecules that exhibit inverse agonism with clinical application have been established. The figure illustrates an example of a dose-response curve with an inverse agonist. Here is a summary of the dose-response graphs. The graph has the concentration of the drug on the x-axis and log scale, and the response, which you may see called Q, on the y-axis. Take a moment to think about which plot represents a partial agonist, an inverse agonist, and an antagonist. The agonist would elicit a full response, represented as 100%. The partial agonist can only induce a fraction of the maximum response, and is therefore less than 100% but greater than 0. The antagonist blocks all signal induction, and therefore has 0 response. The inverse agonist elicits a response opposite of that of the agonist, and is therefore below 0. It may help to think of these agonists binding to a receptor that has a basal level of activity. When a full or partial agonist binds, the response goes up. When an antagonist binds, the response stays the same, while when the inverse agonist binds, the response goes down. Here is an example of different opioids. Morphine or methadone are full agonists, and therefore can trigger a maximum analgesic effect at the mu-opioid receptor. Buprenorphine is a partial agonist, so it will never trigger a response as high as morphine at high concentrations. This is really important to know if you are administering pain medication to a patient, and you think you might need to up the level of analgesia you need to give. If you give buprenorphine first, and then decide your patient's pain is too much and you need to give morphine, you are out of luck, since buprenorphine binds mu receptors tighter than morphine. You will have to wait for the patient to remake mu receptors in the absence of buprenorphine in order for morphine to work. Here is a summary graph looking at what happens when we add an inhibitor to a system with an agonist, which has the response labeled A. We again have the response on the y-axis and the log of the drug concentration on the x-axis. Let's compare responses B and C to A. If we add a competitive inhibitor to the system, we can still reach a maximum response, B, given enough time and a high enough drug concentration. If we add a non-competitive inhibitor to the system, the overall maximum effect of the drug goes down, even at high concentrations, as is seen with response C. Make sure you can draw out each of these responses and explain why curves B and C are different from curve A.